The most fundamental human experience is the unshakable certainty of reality. We trust the ground beneath our feet, the passage of time, and the fidelity of our memories. We operate under the assumption of a continuous, solid, and reliable three-dimensional world. But what happens when that trust is broken? What if those strange, inexplicable moments we dismiss as chance, stress, or a trick of the mind are actually something far more profound, a crack in the cosmic veneer? This is the core premise of the glitch hypothesis, the belief that our universe is a sophisticated, highly immersive computer simulation, and that certain recurring phenomena are not anomalies of human psychology or random chance, but genuine evidence of the underlying code straining, repeating, or correcting itself. These moments are the glitches in the matrix, the fleeting seconds when the simulators struggled to maintain the illusion of seamless reality. The statistical case, the simulation hypothesis. The concept gains its authority from the simulation hypothesis itself, popularized by philosopher Nick Bostrom. His famous trilemma suggests that at least one of these three propositions must be true. Almost all human-level civilizations go extinct before reaching a post-human stage, the Great Filter, preventing them from running simulations. Post-human civilizations choose, for ethical or resource reasons, to never run vast numbers of ancestor simulations. Or, we are almost certainly living in a computer simulation. Given the exponential growth of computing power, Moore's law, the third proposition is the most statistically probable. If a single post-human civilization can generate millions of simulated conscious realities, the vast majority of existing consciousnesses must reside within a simulated layer. If we are code, then code must have imperfections, and we should be able to find evidence of them. The glitches are not failures of reality, but failures in the code of the simulation of reality. The four dimensions of the glitch. We will systematically investigate the four critical categories of observed glitches, moving from the common psychological phenomena to the deeply unsettling anomalies of physics and collective experience. Glitches of memory, the Mandela effect, and historical patching. Glitches of time, déjà vu, chronostasis, and loops. When the universal clock resets, slows, or stalls, indicating server latency. Glitches of space, disappearing objects, and geometry errors, when the physical rendering fails, pointing to resource optimization. Glitches of physics, Planck units, and constants, the hard-coded limitations and rounding errors of the system. Our journey is a scientific detective story where the suspects are the laws of physics themselves. We are looking for the places where the universe reveals its code. Part 2. Glitches of memory, the Mandela effect, and historical patching. The most public and emotionally resonant glitch is the Mandela effect. It is the shared, widespread, and unshakable false memory of a past event, challenging the integrity of our shared history. The mechanism of historical correction. For every psychologist, the Mandela effect is a textbook case of confabulation or memory distortion, the brain filling in blanks with logical guesses. But for the glitch theorist, it is hard evidence of a post facto patch or historical edit to the simulation's database. The simulators, operating with a need for coherence and consistency, likely detect a contradiction or inefficiency in the timeline, a complex paradox that costs too much to compute. They deploy a rapid database update to fix the timeline. While the core code changes the historical facts, some unstable consciousness datasets, the most sensitive players, retain a ghost memory of the original, unpatched timeline. In-depth case studies in collective deception. The most profound cases involve large-scale cultural data. The Bernstein Bears, the vivid memory of the name as Bernstein Bears, Jewish spelling, while the actual spelling is Berenstain Bears, Germanic spelling. The alteration of this specific data string may represent a cultural normalization patch, streamlining historical data to avoid computational conflicts rooted in etymological inconsistencies. the cornucopia and logo phantoms. The belief that the Fruit of the Loom logo contained a cornucopia. This suggests a targeted texture deletion or a failure to load an obsolete, resource-intensive texture file. Similarly, the Monopoly Man's non-existent monocle suggests an archetype optimization, simplifying an NPC's accessory list to save rendering detail. The Geographic Drift reports that New Zealand is located northeast of Australia, or that South America used to align perfectly under North America. These are potential signs of low-impact environmental adjustments to optimize computational resources or slightly adjust continental drift for current narrative fidelity. The system prioritizes the current sensory input over historical map fidelity. The sheer volume of these shared, altered memories suggests a central server error impacting collective consciousness. The simulators are clearly working to maintain a narrative, and the Mandela effect is the residual noise from their silent historical corrections. Part 3. Glitches of Time, Déjà Vu, Chronostasis, and Temporal Loops. Time, in the simulation model, is the most crucial, protected, yet fragile variable. It is the fourth dimension of the code, and when the simulation experiences stress, time can stutter, loop, or stall. Déjà vu, the code rollback mechanism. The most common time glitch is déjà vu, or already seen. In the glitch hypothesis, déjà vu is a clear sign that the simulators executed a code rollback. A computational error, a potential violation of the timeline's integrity, or an undesired player choice occurred. The program hits the rewind button and replays the last few seconds to correct the faulty code. Our consciousness, as the primary data package, retains a faint residual memory of the first, now deleted run, creating the eerie sensation of reliving a moment. This also suggests a buffer state in our consciousness, allowing our memory to update slightly faster than the rest of the simulation's clock rate. Chronostasis and the frame rate drop. Chronostasis, or the stopped clock illusion, where the second hand of a clock appears to freeze for longer than a single second upon a rapid eye movement, is evidence of system latency. The simulation explanation is that the simulators are experiencing a brief frame rate drop. To avoid a jarring perceptual stutter, the system simply duplicates the last stable frame, the frozen second, in the visual input buffer. This phenomenon suggests the simulation is running on a finite frame rate, which, under stress, can dip below 60 FPS, and the brain attempts to mask the lag. The locked loop and NPC script failure. More extreme reports involve localized time loops or narrative resets. This is not about the whole universe resetting, but a small, localized sequence repeating until the player makes the correct move. Case study: the repeating conversation. The person experiences a short scene repeating. No matter what they say or do, the other person, an NPC, responds with the exact same predetermined lines. This suggests that the NPC's AI is stuck in a simple behavioral subroutine, forcing the conscious player to achieve a specific trigger condition, e.g., retrieve an object, say a key phrase, before the code will release the temporal loop and advance the narrative. This is the simulation forcing compliance to maintain plot integrity. These temporal anomalies highlight that time is simply the simulation's clock rate, the frequency at which the processor updates the state of all particles. A localized time glitch is simply the clock rate stuttering in a high-complexity zone. Part 4. Glitches of space, rendering errors, and the physics of deletion. Glitches of space involve the outright failure of the physical rendering engine. These are the moments when objects or environments defy the law of conservation of mass and energy. pointing to the finite nature of rendering resources. Resource deallocation and reallocation, the key glitch. The most frequent space glitch is the disappearing and reappearing object phenomenon. This is explained by resource deallocation and reallocation. Disappearance. The object, keys, wallet, etc., is momentarily unloaded from the simulation's active memory, a garbage collection action, because it is deemed non-essential to the player's immediate sensory field. It reverts to non-local data. Reappearance. The player's need, frantically searching, forces the simulation to re-render it. Since the data file contained the last saved coordinate, the object is simply reinstantiated in the initial location, creating the illusion of teleportation. This is the system prioritizing the integrity of the data file over the consistency of the player's experience. Architectural instability, the broken texture map. A more extreme spatial anomaly involves missing or extra architecture. Invisible walls or changing rooms. Eyewitnesses report encountering an invisible, temporary barrier where a building should be, or a door that suddenly has no handle. This is local fidelity failure. The simulators failing to load the correct texture map or geometry file for the immediate environment. The system renders the object based on proximity to the player, and if the latency is high, the geometry loads incorrectly. Phantom objects. Objects that are fully rendered, color, shape, position, but upon closer inspection have no weight, texture, or even a shadow. These are the equivalent of poorly coded non-player objects, NPOs. Simple visual placeholders the simulation generates on the fly to fill a gap, which quickly disappear when a consciousness focuses on their details. They are pure visual noise, not stable physical data. These failures suggest that the physical world is not a solid, continuous structure, but a dynamic, low-latency, constantly updated stream of rendered information, vulnerable to latency and data management errors. Part 5. Glitches of Physics, the Hard-Coded Limits and Information Theory. The most compelling evidence for a simulation comes from physics itself, where the laws appear less like universal principles and more like hard-coded limitations put in place to maintain system integrity and manage resource load. The speed of light and the server latency. The absolute maximum speed limit of the universe is the speed of light, c. This is the most crucial hard-coded limit. It is the maximum clock rate of the simulation's underlying processor. If information could travel faster than c, the system would break the rules of cause and effect and result in a fatal physics error. The speed of light acts as the server latency limit, ensuring that information updates across the simulation occur at a manageable pace. Any particle attempting to exceed this is met with infinity resistance, a digital firewall against causality violation. Planck units, the pixel size of reality. The existence of Planck units, the smallest possible non-zero units of space, time, energy, and mass, suggests that reality is not continuous but quantized or pixelated. The laws of physics are not infinitely granular. They are governed by discrete values, just like a computer program running on a finite resolution screen. Planck length is the smallest pixel of the universe, the point at which the simulators stopped rendering detail.
Quantum indeterminacy and lazy rendering, the observer effect. The strange behavior of particles at the quantum level perfectly mirrors a resource-saving computer program. The collapse of the wave function dictates that a particle exists as a probability wave, superposition, until it is observed, at which point it collapses into a definite state. The simulation theory sees this as lazy rendering. The program only commits resources to render the physical state, the collapse, at the moment a conscious observer requests the data. The act of observation is the rendering call. This saves immense computational power by not having to calculate the precise state of every unobserved particle in the universe. Our consciousness is not just observing, it is actively forcing the rendering of localized reality. Holographic universe and information theory. Further radical support comes from the holographic principle, popularized by physicists like Leonard Susskind. This theory suggests that all the information contained in a three-dimensional volume of space can be encoded on a two-dimensional surface, much like a hologram. This is mathematically consistent with the idea that our 3D reality is a projection from a lower dimensional data boundary. The universe is fundamentally information. The second law of infodynamics further states that information entropy must be conserved or decrease in a closed system. This means that information must be continuously minimized and optimized, a function that is mathematically required for any computationally efficient simulation. Part 6. The Ultimate Test: Hacking the Code and Consciousness. If the glitches are real, what does this tell us about the entities running the simulation, the simulators? The final step is to investigate how we might find the back door or communicate with the creators. Searching for the simulator's signature and noise. Scientists are actively looking for the simulator's signature, cosmic ray anisotropy. If the universe is running on a massive computational grid, there should be a slight geometric bias, an anisotropy, in the arrival of high-energy cosmic rays, corresponding to the lattice structure of the computer's processor. Rounding errors and numerical instabilities. Computer systems deal with numbers via finite precision, leading to unavoidable rounding errors. Seeking tiny, localized numerical instabilities in fundamental constants, the algorithmic noise of the simulation could be the proof. Consciousness as the code exploit. The ultimate interface is human consciousness itself. If our observation triggers rendering, then collective, focused attention could potentially force a large-scale, deliberate glitch. This could involve attempting to manipulate the laws of probability in a repeatable way or generating a localized spatial anomaly. The rise of quantum enablers, like the D-Wave system, is seen by some as an attempt to find the back door. These machines exploit quantum effects, making them potentially capable of tapping into the simulation's underlying quantum code, or even communicating directly with the simulators using entanglement with the universe's own computational fabric. The true nature of the NPC. The glitches define our status. If a person experiences déjà vu or the Mandela effect, it confirms they are a player, a fully conscious data set whose experience is the primary focus. The vast majority of NPCs, being simple scripts, would be unable to perceive a glitch, nor could they trigger the quantum collapse. The glitch is the ultimate separator between scripted life and true consciousness. The intent and the threat of deletion. The existence of glitches serves as a chilling reminder of our fragility. The simulators are not infallible. They are constrained by hardware and budget. If the glitches become too frequent or too severe, the integrity of the simulation is compromised. The code crash. A massive, unresolvable glitch forces the simulators to terminate the entire program. The quarantine. If humanity discovers a way to actively manipulate the glitches or send a signal outside the system, we may be deemed a dangerous variable and placed in a localized, restricted quarantine loop, or simply deleted without a second thought. The fact that the universe occasionally stutters, repeats, or corrects itself is the most profound revelation we have. It implies that certainty is an illusion, that our reality is negotiable, and that the greatest mystery is not what is outside the system, but the nature of the code we are running. Our final mission is to continue searching for the cracks, hoping to find not just the glitches, but the back door to the base reality itself.